The primary objective of this experiment is to calculate and determine the acceleration due to gravity by analyzing centripetal force on a rotating mass. By varying the radius, we are able to collect the data that we needed to calculate the acceleration due to gravity using the centripetal formula.
Now the theory of which this experiment is based on. This experiment revolves around the force necessary to keep an object moving in a constant circular path, the centripetal force. According to Newton's first law of motion, there must be forces acting on an object moving in a circular path, since it does not move off in a straight line. The second law of motion, F equals ma, also indicates forces, a pair of forces, since an unbalanced force is required to change the motion of an object. An object moving in a circular path is continuously being accelerated, since it is continuously changing direction. This means that there is a continuous unbalanced force acting on the object that pulls it out of a straight line path. The force that pulls an object out of a straight line path and into a circular path is called a centripetal force. The second force paired with this centripetal force is the force the object being spun exerts on the string in this experiment. This vector is pointing away from the center of rotation. The magnitude of the centripetal force required to keep an object in a circular path depends on the inertia, or mass, and the acceleration of the object. As understandable from the second law, F equals ma, the acceleration of an object moving in uniform circular motion. From this equation, it can be understood that by increasing the radius of the spinning object, the acceleration decreases as the denominator increases in magnitude. Hence, the velocity of the object, the period of the object's rotational motion, and centripetal force required to keep the object rotating decreases. Based on the diagram, and according to Newton's third law of action and reaction, the other pair forces that exist above is centripetal force required to keep the rubber stopper rotating, which is equal to the weight of the weights. This can be expressed with the equation below. F centripetal equals mass of the weights times gravity. This equation can be rearranged using the equations for circular motion and inserting m1 as the mass of the rubber stopper, as well as m2 as the mass of the weights.
Shown here are the variables of this experiment.
Materials and apparatuses are always needed in experiments. They are the objects needed to calculate or actually do the experiment. These materials, for this experiment at least, are strings, rubber stoppers with the weight on the end of the string that experiences circular motion, weight, tube, or a pipe. And for the apparatuses for the experiment, it would be a triple beam balance, camera and tripod for recording footage, stopwatch, and a meter ruler.
And now on to the procedure of the experiment.
First of all, mark the string for radii 0.1, 0.2, and so on until 0.6 meters. These markings will be used as indicators for the experimenter to keep track of the spinning rubber stopper and make sure that it spins stably in a relatively constant period and in an unchanging radius. Second, measure the mass of the rubber stopper and weight using the triple beam balance. Third, attach the rubber stopper to one end of the string protruding from above the tube, with one of the radii markings also correctly aligned with the bottom of the tube, and the weight on the other end of the string. 4. The person spinning will spin the rotational object for 50 revolutions, and the timekeeper will keep track of how long it takes to reach set amount of spins in seconds with a stopwatch. 5th, repeat the process for each of the different radii of the strings, with each radius having it done twice.
We will delve into this data obtained from the experiment on determining the acceleration due to gravity using centripetal force. Before we dive in, it is important for us to understand how we gathered this data. The data collected from the experiment primarily consists of the time it took for the experimenter to spin the rubber stopper 50 times. This time was recorded by another experimenter using a stopwatch to ensure accuracy and eliminate any potential human error in timing. It's worth noting that we employed a redundancy measure by having two experimenters count the number of rotations the rubber stopper had made around this person spinning it. This double-checking procedure was implemented to enhance our reliability of our data and minimize the likelihood of discrepancies.
The following is the data recorded from the experiment. For the radius of 0.1 meters, The time it took for the rubber stopper to rotate 50 times is 16.6 seconds. Dividing that by 50 to get the time for one rotation, or the period, results in 0.332 seconds, rounded to 3 significant figures. The method for obtaining the period is the same for the rest of the radii. Then, as mentioned before, a scatter graph will be plotted with the y-axis consisting of period squared, t squared, the dependent variable, and the x-axis consisting of the change in radius m, the independent variable. The resulting gradient is 0.728137582.4, which is the value of t squared over r that will be substituted to the equation explained in the theory to obtain a value for gravity.
The gravity of the Earth was able to be calculated from the rotational motion experiment, resulting in a 9.47 meters per second squared, and therefore a 3.46% error compared to the standard actual value of 9.81 meters per second squared. This result can be considered accurate because it is under the 5% margin of error. Errors that could have contributed to the deviation of the acceleration of gravity calculated from this experiment include systematic errors, random errors, and human errors.
Perhaps in the future, more repetitions can be done to compare and average the results for the gravitational acceleration, and maybe for more accurate results, the act of spinning the object to be controlled by something like a robot, ensuring that there are less variations in the force and direction of the rotation.
Overall, the experiment was a success at measuring the gravitational acceleration caused by the Earth, and it had led us to maximize the precautions needed to always have maximal accuracy in the experiment. This would help other people that would try to recreate the experiment to get better results.